Nyquist Stability Criteria is invented by Nyquist, and the Nyquist plot is also called as a frequency response plot, and the purpose of drawing this plot is to determine the stability of closed loop system from the given loop transfer function, and from this plot we can actually have number of closed loop poles. We can invent the number of closed loop poles in right half of the plane. With that you can assess the stability of the system, and next we can actually to determine gain margin, phase margin, and gain margin at phase crossover frequency and phase margin at gain crossover frequency, and we can determine the relative stability of the system, and further we can determine the range of k, that is gain constant, from this plot, and range of k value from the plot. So this many advantages we have from the Nyquist stability criteria. So the complete frequency response plot, the plot is complete frequency response plot for given loop transfer function. And this Nyquist stability criteria, basically it works based on principle of argument. So what is this principle of argument? Suppose the S-plane there are certain poles and zeros. Say some poles and zeros are covered by the closed path in the S-plane. Say this pole is covered in the clockwise direction. There will be a corresponding plot in G of S into H of S plane. Suppose a pole is covered by the closed path, then if you map every point on this path, when you map into G of S into H of S plane, then around the origin there will be a path in anti-clockwise direction. So when the pole is covered in the S plane by a closed path, then it encircles the origin in G of S into H of S plane. So that means n is equal to number of encirclements about the origin in G of S into H of S plane equal to 1. Suppose in the S plane, say there are two zeros in the left half of the S plane and they are covered by a closed path. Then if you map every point into g of s into h of s plane, g of s into h of s plane, there will be encirclements in clockwise direction, two types. It is 1 and 2. Because it is now in clockwise direction, then I write n is equal to minus 2. That means the number of poles and zeros in the S-plane are covered by a closed path, then there will be corresponding encirclements in g of s into h of s plane by a mathematical relation according to principle of argument n is equal to p minus z. So in this case, when you see there are two zeros and there are no poles covered by the closed path, so p is 0 and there are two zeros here, so it is minus 2. So I say that n is number of encirclements around the origin as minus 2 because it is in clockwise direction. Suppose if there are two poles, covered, enclosed in the S-plane, then there will be corresponding path in the g of s into h of s plane. Being a poles here covered, there will be two encirclements about the origin in counterclockwise direction. So depending on the poles and zeros covered in the S-plane, the corresponding encirclements n in the g of s into h of s plane varies. So that is given by the mathematical relation here, n is equal to p minus z, where p is number of poles covered here are 2 and no zeros in this S-plane, so n is equal to 2. So the difference between n is equal to plus 2 and n is equal to minus 2 is only the direction. So counterclockwise direction is considered as a positive plus, so number of encirclements about the origin are 2 when there are two poles covered in the S-plane. Suppose in the S-plane, say there are 3 poles and 1 0. So this is covered in a clockwise direction, a closed path we say. Then you can see here the number of poles covered by that path are 3 and number of zeros are only 1. So when you see that equation according to principle of argument, n is equal to p minus z, so it is 3 minus 1, it is equal to 2. So the number of encirclements in g of s into h of s plane about the origin are 2, and if it is a plus 2, then the encirclement will be in counterclockwise direction. And it goes like that. If you have 1 pole and 1 0, this is covered in the S-plane, then you can see that p is equal to 1, z is also equal to 1, and the number of encirclements is equal to p minus z is equal to 0. So in the g of s into h of s plane, there will be a encirclement but not about the origin, because this is according to principle of argument, n is 0 here, but there will be a corresponding path for this S plane in g of s into h of s plane. So it is not our interest, because according to Nyquist Stability Criteria, we are interested about the number of closed loop poles which lie in the right half of the S plane will indicate us whether the system is stable or not. So that is our interest, and we will apply this n equal to p minus z for a given loop transfer function. So to explain better about Nyquist stability criteria, and as I said, to determine the stability of the closed loop system, our interest is to know the number of closed loop poles which lie in the right half of the S-plane. Nyquist defined its own contour, Nyquist contour, of S-plane, that he covers from origin towards imaginary axis plus j infinity, then he covers the negative imaginary axis also up to minus j infinity, then the entire right half of the S-plane, the entire right half of the S-plane with this way, this is called Nyquist contour. This is called Nyquist contour. So what he does here is he tries to cover the entire right half of the portion, like from 0 to plus j infinity, and this is up to minus j infinity. So the entire imaginary axis is covered, and then the entire right half of the S-plane, because our interest is to see if there are any closed loop poles in the right half of the S-plane, then we can say that it is an unstable system. So that is the way he tries to cover the entire right half of the portion by having the radius of this semicircle as r tending to infinity. So whenever we map this every portion of the Nyquist contour into g of s into h of s plane, we substitute in g of s into h of s function where s value as r e power j theta to cover the entire right half of the portion. This r is the radius tending to infinity, and the theta value it from this is plus 90 to minus 90. Theta varies from plus 90 to minus 90. So this is the way he tries to cover the entire right half of the portion, then assess the stability. So when you look at here, there are three portions. One is from 0 to plus j infinity. So what is the meaning of, there are three sections in the Nyquist contour. Call this section as C1 and call this the semicircle as C2 and call this portion as C3. So there are three sections, C1, C2 and C3. Now all these three sections must be mapped into g of s into h of s plane and look at the encirclements around the origin. But here when I say the mapping means every portion of these three sections into g of s into h of s plane. So the encirclements not around the origin, because as you know that the characteristic equation 1 plus g of s into h of s equal to 0 is the characteristic equation. So g of s into h of s is equal to minus 1. This point is nothing but minus 1 plus j0, or it is 1 at an angle of minus 180 degrees. So when you map C1, C2, C3 into g of s into h of s plane, the critical point is not about the origin but about minus 1 plus j0 point. That means when I say now if the Nyquist contour is covered, then the critical point is not about the origin, but in g of s into h of s plane, it is minus 1 plus j0 point. So we must look for the principle of argument in Nyquist stability criteria for the critical point of minus 1 plus j0, but not the origin. This is according to the characteristic equation. Now we will see that how this C1, C2, C3 are mapped into g of s into h of s plane to assess the closed loop system stability. So some mathematical treatment before actually mapping these three sections into g of s into h of s plane. Let us consider the loop transfer function g of s into h of s. We write this as k into numerator function by denominator function. N of s is a numerator function and d of s is a denominator function. Call this as equation number 1. Now, if this is a loop transfer function, the closed loop transfer function becomes g of s by 1 plus g of s into h of s. So this can be g of s by 1 plus, you can replace g of s into h of s by this function k into n of s by d of s. This can be written as g of s into d of s by d of s plus k into n of s. So you can call this equation as 2, the closed loop transfer function. And as you know that the denominator part of the closed loop transfer function is known as characteristic equation. This is equal to 1 plus g of s into h of s. This is the characteristic polynomial or equation. You can call this as q of s. So this can be, this q of s means it is a characteristic equation 1 plus k n of s by d of s. So this can be d of s plus k into n of s by d of s. Call this as equation number 3. Equation 1 depicts the loop transfer function. Equation 2 closed loop transfer function. Equation 3, the characteristic equation, is nothing but denominator of the closed loop transfer function. When you compare equation 1 and 3, when you compare equation 1 and 3, the poles, you can see the denominator term, it is d of s, and even in the equation 1 it is d of s. So the poles of characteristic equation is nothing but loop transfer function poles. This is the conclusion we can arrive, that poles of the characteristic equation is nothing but open loop transfer function poles. And when you compare equation 2 and 3, here the zeros of characteristic equation, that means the numerator term, zeros of characteristic equation is nothing but the poles of closed loop transfer function. Poles of closed loop transfer function. Now, with this understanding, we will consider the principle of argument n is equal to p minus z. Here, what you should consider p, what is z for stability of the closed loop system in the Nyquist stability criteria. Very important to remember that p here is nothing but poles of characteristic equation in right half of the S-plane, because that is our interest, to know the poles of characteristic equation in right half of the S-plane is nothing but open loop transfer function poles. This we need to identify from the open loop transfer function. Poles is nothing but poles of the characteristic equation in the right half of the S-plane, that is considered as P. What is Z then? Z is the zeros of characteristic equation in the right half of the S-plane. Zeros of characteristic equation in the right half of the S-plane is nothing but closed loop transfer function poles. So once you understand this P and Z in terms of characteristic equation, poles and zeros, to open loop and closed loop transfer function poles, then N. What is N? N is the number of encirclements. So according to the principle of argument, N is equal to P minus Z, where P is number of poles of open loop transfer function in the right half of the S-plane, and Z is the number of zeros of characteristic equation, nothing but closed loop transfer function poles lie in the right half of the S-plane. Then N will be number of encirclements around the critical point. The critical point in G of S into H of S plane is not origin, remember, it is minus 1 plus J0. This point is the critical point. Sometimes we call it as 1 at an angle of minus 180 degree also. So we should look for the number of encirclements in the Nyquist plot to assess the stability of the system. Now when you look at this, the Nyquist contour for a given loop transfer function, what is the mapping? Meaning you need to map the section C1. That means this entire line, every point on this 0 to plus j infinity should be mapped into G of S into H of S plane is nothing but polar plot. We draw the polar plot. Polar plot is a frequency response plot, varies omega when omega is varied from 0 to infinity. So C1 section mapping into G of S into H of S plane is nothing but polar plot. Once you draw the polar plot, it is understood that the mapping of C1 section is done. Now let us look for the other section, that mapping of section C2. It is a very infinite semicircle, and the value of S here, the value of S is equal to R e power j theta, where the radius of that semicircle is infinite, very high, and the theta limits from plus 90 to minus 90 here. This S value we should substitute in the given G of S into H of S. So that way the mapping of section C2 is done, replacing S in the given loop transfer function by S is equal to R e power j theta with limits theta plus 90 to minus 90, and then corresponding mapping should be done into G of S into H of S plane. Now what is left here is mapping of section C3. Mapping of section C3. So when you look for the frequency axis, this is a negative imaginary axis. So section C3 from omega, okay, minus infinity to 0. So that means you have seen that omega equal to 0 to infinity as a polar plot for mapping of section C1. Then mapping of section C3 is nothing but image of the polar plot. Image of the polar plot is nothing but mapping of section C3. So this way all three sections must be mapped into G of S into H of S plane. Then you should look for the number of encirclements, that n is equal to, are there any poles of open loop transfer function lie in the right half, and are there any closed loop poles lie in the right half of the S plane. So with this we will come to know the stability of the closed loop system from the Nyquist plot. This Nyquist contour can be considered for the problem G of S into H of S is equal to some function like this, some poles and zeros as S plus 3 into S plus 4, something like this. So this is well valid. You need to draw the Nyquist contour, then draw the polar plot for this, then draw the image of the polar plot for this, then replace S by R e power j theta in this. Then you can look for the, you can assess the stability of the closed loop system. For example, if G of S into H of S is given by a function, but there is a pole at origin. When you compare to this, there is a pole at origin now, and you have a function like this. So the Nyquist contour is not valid when you have a pole at origin. So what he does here is, the Nyquist contour aim is to cover the entire right half of the portion and the imaginary axis. But if there is a pole at origin or on imaginary axis, Nyquist did bypassing of the Nyquist contour. That means if there is a pole at origin here, then he bypass it, that pole at origin, then the Nyquist contour for this will be like this. Section C1 and section C2 and section C3. All these three sections are similar to the example without pole at origin. But because of the pole at origin, the Nyquist contour has got 4 sections. The fourth section is this one, C4. So there are 4 sections. If you find a pole, 1 pole or 2 poles or 3 poles at origin, we must bypass it, consider that portion as C4 in the Nyquist contour. So there are 4 sections now, C1, C2, C3, C4. Mapping of C1 is nothing but polar plot. Mapping of C2, as I said, it is a infinite radius you are considering, and S value in the given loop transfer function should be replaced by R e power j theta, where the radius is tending to infinity. Next, the C3 section is image of the polar plot. Mapping of C3 section is image of polar plot. Now the very important one, the fourth section, C4, when you map this into G of S into H of S plane, again you have to replace S by a value called rho e power j theta, where rho is the value tending to 0, because it is only a bypassing the pole at origin. A small portion means that radius of that small semicircle is considered as tending to 0, but the limits are from minus 90 to plus 90. So when you look at this mapping of section C2, there are limits here for theta from plus 90 to minus 90, plus 90 to minus 90, but here also you have a theta in the function. That limits are from minus 90 theta to plus 90. So this is the way we should do mapping of the 3 or 4 sections depending on the loop transfer function, and then assess the stability of the system. So to assess the stability of given open loop system and closed loop system, say this is S-plane. For open loop system stability, the open loop poles in the right half should be equal to 0. This is nothing but the poles of characteristic equation. Poles of characteristic equation should be equal to 0, that is P equal to 0. For open loop stability, there should not be any pole in the right half of the S-plane for the given open loop system. That means, as you know the equation, n is equal to P minus Z. So when you substitute P equal to 0, n should be equal to minus Z for open loop system stability. When you look at the closed loop stability system, closed loop poles must be 0 in the right half of the S-plane. It is nothing but zeros of characteristic equation equal to 0. That means Z should be equal to 0 in the given equation, n is equal to P minus Z. So when Z is 0, n should be equal to P for closed loop stability. So n should be equal to minus Z for open loop system stability, and n should be equal to P for closed loop system stability. So the meaning, we can conclude that for open loop system stability, there should not be any open loop pole in right half of the S-plane, that means P should be equal to 0, so n must be equal to minus Z for open loop system stability. Similarly, for closed loop stability, there should not be any closed loop pole in right half of the S-plane. That is nothing but zeros of the characteristic equation, that Z should be 0. So we can say that n must be equal to P for closed loop system stability. So the criteria statement according to Nyquist, criteria statement can be given this way: the number of encirclements about -1 plus J0 critical point, number of encirclements about -1 plus J0 critical point must be equal to the number of poles of characteristic equation which are nothing but open loop transfer function poles in the right half of the S-plane. Right half the S-plane. That means n should be equal to p. Then only the z will be 0. So this p can be directly obtained from the given loop transfer function. So only thing we need to see that when you map the each and every section of Nyquist contour, we must focus on the number of encirclements. So if there are no poles in the right half of the S-plane from the given transfer function, then there should not be any encirclements about -1 plus J0 critical point. Then we can say that it is a stable system. If p is equal to 1 or p is equal to 2, say 2 poles in the right half you find from the given loop transfer function, then n also must be equal to p, that is equal to 2. So z will be 0. We say that it is a stable system.